Hey everyone and welcome to PrepFusion. I'm Anish and today we'll start the lecture 7 of time domain analysis. So in this lecture what we'll do, basically firstly we study the performance parameters of second order systems. Then after that I will give you a few assignment questions, and if time permits we'll also study the analysis of those parameters of second order system itself, underdamped system, by varying the poles, right? By varying the location of the poles, we'll see how my parameters vary. Okay, so we'll see that. So this is the first parameter for a second order system, that is basically the rise time. Do note that most of the parameters are for like unit step response of a stable second order underdamped system. Okay, so most of the parameters are for this one only. So for other type of damping I will strictly specify that one. Okay, so mainly we analyze underdamped systems only. Okay, because practically we get it's easy to build a underdamped system, right? That's why critical damp is very difficult, because it's for a particular condition, right? And overdamped we don't want, because our response becomes slower, right? That's why we use mostly underdamped system. That's why we want to measure the parameters of mostly underdamped system. Okay, so what is the rise time? Basically in the first order system, right, what was the definition? It was basically from 10% to 90%, right? But what is the definition for rise time for a second order system? Okay, this is valid for a second order underdamped system, right? Okay, so it is the time taken for the system to reach 100% of its final value for the first time. Okay, for the first time. Basically, like what happens in an underdamped system, it oscillates, right? Oscillates. Okay, it sometimes goes over its steady state, then again comes back down, then again goes over, right? So it is a time taken for the output, like this output, to reach 100% of its final value for the first time. So from the graph, tell me, when does it reach 100% of its final value for the first time? At this point, right? At this point it reaches 100% for the first time. So this will be my settling point, right? No, sorry, rise time. Okay, T-rise. Okay, so this will be my rise time for a underdamped system. Now, like the definition changes a bit for a critical time system, and you don't need to remember that, because that won't come anyways. But still, for a critical time system, right, the output response, the time taken for the system to go from 5% to 95% of its final value, that is known as the rise time for critical time system. Okay, and for overdamped system, it is basically from 10% to 90% of its final value. As like overdamped system, we can approximate it as first order only. So the definitions for overdamped systems are similar to the first order only. Okay, so you can relate with first order system. So for overdamped, it is 10% to 90%. Okay, and basically we can relate this one with first order system. Okay, so yeah, this is basically for the overdamped system. Now let me derive the rise time expression, right? So what is the definition? It has to reach 100% of its final value. Now what was the equation for the underdamped output expression, right? It was basically CT. I will write the generalized expression, that is A into K. A is the amplitude of the unit step and K is the d second of the system, right? Okay, I hope you remember. You have to remember this one, there is no other option. Okay, so this is one. How do you remember this? You know, this comes with the time constant, that is 1 by zeta omega n, which comes in inverse here. So this is 1 by zeta omega n, and this is basically under root one minus zeta square. This comes down, right? And this is sine. Okay, there will be damped frequency and there will be some theta. Okay, so this is my expression basically. Now for like, what do you know, what information do you know? So at t equals to t rise, my output, okay, this is not c of t, this is y of t actually. my output will go to AK, right? My output will go to AK. Okay, so I will put the value of AK here, and I will put T equals to TR, right? So AK equals to TR divided by 1 minus zeta square TR. Okay, so this is this case. So what I will do, simply this will get cancelled out, right? This I can cancel. Okay, so this will become 1, and 1 will also get cancelled. So this one will get multiplied with, okay, let me write this expression. So what will be my expression? I will get this equals to 0, right? This will be equals to 0, hence my sine omega d TR plus theta should be equals to 0. Now when can this be 0, right? Okay, it can be 0 at TR equals to minus pi over omega d, but that means my time is negative, right? That is not possible. Like, it started from t equals 0. Okay, so what is the next time this whole expression becomes 0? So sine 0 is 0, then sine pi is 0, right? So I also have to find the first instant, right? First instant. So sine pi will be the first instant when this reaches 0. After that, obviously sine 2 pi is also 0, but that isn't the first instant. But our definition says that it has to reach its final value for the first time. Okay, so yeah, let's see. So this should be equals to omega d TR plus theta equals to pi, right? So my TR equals to pi minus theta by omega d. Okay, so this is my rise time derivation, right? Rise time derivation. So you have to remember this. Okay, these are important formulas, so you have to remember this. Obviously you won't be able to always derive this because this will take time, so you have to remember. Just by practicing more and more questions, you will get this in your head, right? So one thing, this is only valid for, I have already told this already, but I will still again say it, that only valid for underdamped system, because obviously we use the underdamped system equation to derive this, right? So this will be only valid for okay. So yeah, now let's do a question. Basically there will understand. So we have to find the rise time of the following system. The system is given like this, and we just have to find the rise time. So how will we find? Simply just find the zeta, omega n, and from there we can find it. We can find theta and omega d also we can find. So let me take a transfer function. So right, so what is my, this is a standard form only. Okay, this is standard form only. So what is my omega n? My omega n equals to this solution. My omega n equals to 1 only. My omega n equals to 1 only. Now what is my 2 zeta omega n? 2 zeta omega n equals to 4, because omega n square equals to 1. Okay, hence omega n is also equals to 1. So omega n equals to 1 and equals to 4. Okay, and now what is my basically, like omega n equals to zeta equals to comes out as 2, right? So what you will do, now you will find theta, and if you go on to find theta, you will get cos inverse 2. Now you are confused, what happened? Okay, what is wrong? So obviously, right, like cos inverse 2 doesn't exist. What is the issue here? So the issue, right, is basically this is a overdamped system, right? Zeta is more than 1. Okay, overdamped system. And what is the rise time for a overdamped system? Basically, right, rise time for a overdamped system is different. It is basically simply similar to the first order system. So for the first order system, my rise time TR was equals to 2.2 tau, right? TR was equals to 2.2 tau. So this is 2.2 times tau. Now what is tau? Tau is basically the inverse of the root, right? But for the overdamped system, what was the root? So these few things you have to keep in mind. Basically, I hope you remember a bit of it. So I had 2 roots, right? So let me write this. What were the roots? my roots were omega zeta n, okay, minus plus under root, okay, this omega n will come outside, omega n zeta square minus 1. This was one of the roots, right, and another one was this simply minus. Now I will obviously choose this one as this is more nearer to the origin. Okay, this will be more dominant, so I'll choose this one. Now what will be my time constant? It will be the negative of this one and inverse of this one, right? So I will put the negative of this one and the inverse of this one, that will be my time constant. So my time constant will be basically this one, right? It will be zeta omega n minus, it will become minus because I have taken negative, under root zeta square minus 1. Okay, so now just put the value of omega n and zeta and you'll get an answer. So basically, right, what this is 2.2 and zeta omega n is 2 only, minus 2 square minus 1, that is 4 square minus root 3. Okay, and okay, let me just I've already calculated it. It's written on the copy, so it's basically comes out to be somewhere around t rise equals to 8.31 seconds. Okay, so this is basically what it comes out to be. I've already calculated it. So like keep in mind, you have to use your gate calculator, right? So whenever you're solving questions or anything, always use your gate calculator. Okay, don't use anything else, because that will only help you precisely like in the exam, actually real exam. Because if you don't practice from now, like you won't be able to practice at the end stage. Okay, so it is very important. So now let's go to the next definition, that is the peak time, right? Peak time. So what is basically the peak time? It is the value at which the system output / response reaches the first peak of its overshoot. So when it reaches the first peak of its overshoot, right, that is basically the peak time. The name suggests itself. Okay, so first peak overshoot. What do you mean by overshoot? Overshoot is basically some value more than the steady state, right? It is overshooting, that means it is going above its steady state. Okay, so yeah, this is basically what overshoot is, right? So this is my steady state value. So now, right, so I should define the overshoot also. Basically, what does overshoot mean? Response goes above steady state value. Okay, so response goes above steady state value. So this is what basically overshoot means. Okay, so now, right, so what is peak time? Basically, peak time is in the graph. Can you tell me what is a peak time? Peak time is at this point, right? It is reaching its first peak at this point. Okay, so this is the peak time, denoted as TP. Okay, this is a peak time denoted as TP, right? So yeah, now how you will find this? How you will find this peak time? So how did you used to find in the peak, right, maxima? How we used to find? We used to make the differentiation 0. Why? Because here, right, what is the slope? Slope is positive, right? Slope is positive. Slowly slope is decreasing. Here the slope becomes 0 and it's become negative, right? So the point where slope changes sign, or the point where slope is 0, that point will be my peak time at that point of time. So what I will do, I will simply take the expression, and I will what I'll do is differentiate the expression and make it equal to 0, and that will give me the TP. Okay, yeah, so let's calculate that basically. So like this is also only valid for a underdamped system, because only this has damping. Okay, and other ones don't have damping. But let's like few times there will be some exception, right? We will see that. Okay, but this is only valid, first of all, this is only valid for underdamped system. Okay, peak time. So now let's derive this. So again, the same expression, right? Y of t. I will not write this, I will just copy this. So y of t is this expression only, right? Now this is a difficult task, so stay with me. So we have to differentiate this, right? To differentiate this, so I have to make y dash of t. Okay, so if I make y dash of t, what do I get? I get this will be ak only, constant will be outside only, this will be 0, okay, and this is u times v, right? So I will do du dt and put this one, and then I will do other one, right? So du dt is what? This is simply minus zeta omega n e raised to power minus zeta omega n t divided by under root zeta square. Now this one will still remain the v1, okay, and I have the other one, okay. I don't have enough space, so what I will do, I will just reduce the size of this one, and so what will be the other term, that dv dash by dt into u. So dv dash by dt, right? So it will be basically differentiation of sine t is cos omega dt, but there will be some omega d also outside, so like this one also come out, right? Chain rule. So this will be here I have already minus sign outside, so what I will do is put a like bracket over here, okay, because I have already minus sign outside. So this will be plus cos omega dt plus theta, and I have an omega d at the outside as well. Also I have this term outside also, right? So I have to write this one also. So do I have enough space? Yes, I think just enough space. So this term will be outside. What is this? This is e raised to power zeta omega n divided by under root 1 minus zeta square, okay. So this is basically my differentiation, right? Now what I will do, my y dash of t will be equals to 0, right? So my y dash of t at tp will be equals to 0 because it will reach maximum peak, right? Okay, so but we have to do one more thing I have to note here is that what thing we have to note, this y dash of t will be equals to 0 also here also, right? Here, okay, here also it will be 0, so it will be 0 multiple times. Here also it will be 0, so we have to eliminate few solutions, right? Let's see how will we eliminate, right? So if you make this 0, what happens? This term, right, this term goes away, right? This term goes away, okay, as it is equal to 0, this term goes away, and we're only left with this one, because this term also goes away, okay, this term also goes away. So okay, let me write here. So what I will do is just copy this one, okay, not even this one, let me write here only. So it is basically sine omega dt plus theta, and I have this minus zeta omega n, and plus I don't have anything here, right? This is gone, but I have omega d here, right? So this is omega d, and this is cos omega d plus theta equals to 0, right? Okay, equals to 0. So now what will be like my tan theta equals to, so my tan theta, right, tan omega d theta. So this one I will take sin theta over there, and so omega d by zeta omega n equals to my tan theta, okay, tan omega d into t plus theta, okay. So now, right, now what we need to do, we need to put obviously t equals to tp over here, right? T equals to tp, okay. So this is basically my omega d tp in theta. Now what is this omega d by zeta omega n? Okay, so omega d is equals to what? Omega d is equals to, I hope you remember, omega d is equals to omega n into 1 minus zeta square. This I hope you remember, right? How we can always use the help of graph, right? So this is my j omega, and this is my sigma, okay. And like, what is this? This is omega d, which is equal to this root, and okay, I should not write there cross sign, this is wrong. So this is my omega d, and this is my minus zeta omega, okay. So yeah, this is what this is, right? So this is my root, right? So here I hope you know, right? You remember that this radius was omega n. Okay, this radius was omega n, and this omega d square plus zeta omega n square was omega n only under root that one. So I have remember. So omega d is equals to 1 minus zeta square. Now, like this one was omega and this one was theta, right? This one was theta. I remember angle of inclination basically. So now, what is my this is omega d tp plus theta. So what is this equals to? This is equals to like omega d by zeta omega n. So this is also equals to tan theta, right? So omega d tp plus theta equals to tan theta itself. I have to remember, right? What is the definition of tan theta? Tan theta is height upon base, right? This is theta and this height is omega d and this base is zeta omega n. So it is height upon base. So it is tan theta only, right? Tan theta only. Okay. So tan theta equals to omega d tp plus tan theta. Now, when does it equals, right? When does it get equal? So obviously, if I put this equals to 0, tp equals to 0, then it satisfies my equation. But obviously, that is not a solution. From the graph or itself, we know at t equals to 0, it doesn't even start. My output doesn't even start, right? So what will be my solution? So one thing we know, tan theta, right? It repeats after every pi, right? It repeats after every pi. So what I can write, tan theta will also be equal to tan pi plus theta. Okay, everything repeats after pi itself. So pi plus theta, okay, and this is equals to tan omega d tp plus theta. Okay, so what will be my tp equals to? So I can relate it like this one. My tp will be equals to omega d tp will be equals to pi. So omega d tp will be equals to pi. So what will my tp equals to? tp will be equals to pi by omega d. Okay, but one thing we forgot, that this formula is generalized, right? It can repeat for n pi, right? N pi plus theta. Okay, tan n pi plus theta will be equals to tan omega dt p plus theta, right? So it repeats after every pi value. So if you plot the tan theta graph, you will see. Okay, so my tp, right? tp will be equals to n pi by omega d. Okay, n pi by omega d. So this is what my tp will be equals to. So now n can be 1, 2, 3. Now you may ask that for what value my actual tp is equals to, right? So for my like what value I will get the peak time. So for n equals to 1, I will get my peak time. Okay, then for n equals to 2, what I will get? I will also get the differentiation 0, but the difference here is the differentiation will be 0 here, right? Okay, it will be 0 here. So this will be my undershoot time. Okay, this will be minima. Okay, I mean minima after getting a peak. That's why we don't call it anything, right? It's difficult to call it anything. So this will be my minima right now. Okay, and this then again the second peak. Okay, this is the second peak and this is the first peak and this is the third peak. Like this it will go on, right? So like tp pi by omega d basically is equals to my first peak, right? Okay, and like if they ask in the question that I have to find the third peak or the first undershoot, right? Undershoot, this was the first overshoot, or you can say overshoot. Now in the question, if they tell you that you have to find the first undershoot, right? So if you want to find the first undershoot, obviously you have to put t equals to n equals to 2. Okay, so yeah, let me write that also. So this is the first undershoot. Okay, so yeah, Then if you put I will do one more example, that TP equals to 3 pi by omega d. Okay, this will be my second overshoot, right? Second overshoot. Okay, so yeah, this is basically what this is. But if you really want to check, right, if you really want to check, okay, mathematically, if you don't have graph and mathematically you want to check, what you will do, you will put this TP value, okay, put this TP value in the double differentiation, right? So you will put this TP value in d square y t by dt square equals to, and you will find, now if this is positive, okay, if this is positive, then this is a minima, and if this is a negative, then this is a maxima, right? So that's how you check, right? That's how you check. So yeah, this was basically the derivation basically for this one. So now let's do one thing. Let's just put this value, okay, let's just put this value in the equation, this TP value in the equation, and let's see what is the maximum overshoot. Okay, this is known as the maximum overshoot, right? So let me like write it like this one. Maximum overshoot. Okay, so this is the maximum overshoot, right? So yeah, now let's calculate the maximum overshoot. So calculation, calculation for maximum overshoot. So like what is my TP1 equals to? So my TP1 equals to, I know like maximum overshoot will occur on the first peak, right? So that is 5 by omega d. So I'll put this output y of TP1, right? Basically y of TP, which is equals to, so this will remain ak, right? And I will have 1 minus this as e raised to power minus zeta omega n t. Now t is pi by omega d. So I'll put here pi by omega d, okay, and this is 1 minus zeta square, and this is sine omega dt, right? Sine omega dt. So omega d is omega d only, and my t becomes pi by omega d plus theta, right? Plus theta. This is my whole expression. So this becomes ak 1 minus, now what is omega what is omega d by zeta omega n? So this is, that's what we just derived right here, right? Okay, zeta by omega omega d by zeta omega n, what was it? This was equals to tan theta, right? Zeta, this omega d is the height and zeta omega n is the base, right? So height upon base is tan theta. Okay, so now what will be the inverse of this one? So what will be zeta omega n by omega d? It will be cot theta. So exactly that is what written here, right? Zeta omega n by omega d. So I can write this as cot theta, right? So this will be e raised to power, pi will be outside, minus pi cot theta. This is 1 minus zeta square, and this is sine of pi plus theta. Now what is pi plus theta? Pi plus theta is, sine pi plus theta is basically minus sine theta, right? So sine, if you see, it is like this one, right? So if I shift by 0 to pi, if I shift by pi, it becomes negative of this one. So this will be minus of sine theta. So what I will write here is minus of sine theta. Okay, so what is my ak equals to? AK equals to 1 plus a raised to power minus pi cot theta under root 1 minus zeta square. Okay, let me write this value, sine theta, right? Okay, so basically this is my answer. Now what is 1 minus zeta square equals to? So can we again change that? So basically, right, so if I again draw the like that j omega axis, sigma j omega axis, so this is my sigma basically, and this is my j omega. Okay, so if this is my j omega, and like my poles lie around here, right? Okay, this is omega d and this is zeta omega n. Okay, let me write this a bit better. Zeta omega n, right? So this is zeta omega n. So basically, right, basically what is my, this is my theta, and where does this 1 minus zeta square come? It's come in this term, right? Omega d equals to omega n into 1 under root 1 minus zeta square. So omega d equals to 1 minus under root zeta square, and I have outside omega n also. Okay, and this zeta omega n equals to omega n itself. So this is this one only. But what can I, this is, what is this one? This length is omega n, right? This is a circle, right? So this length will be omega n only, omega n. Okay, so I can take the ratio of this basically omega, like this omega d by omega n. So what will I get? I'll get this ratio, right? Omega d by omega n. Okay, I'll put this omega n here, and this will be equals to my 1 minus zeta square, right? Zeta square. So I observe this one here, right? Now what is my omega d by omega n? This is height upon hypotenuse. Okay, height upon hypotenuse. So what is this? Height upon hypotenuse is sine theta, right? It is sine theta. So this is theta, this is theta, so it is sine theta. So my sine theta equals to height upon hypotenuse, which is equals to omega d by omega n, which is equals to under root 1 minus zeta square. So what I will do is I will replace this 1 minus zeta square with sine theta, and what I see is the sine theta is getting cancelled, right? So my sine theta is getting cancelled. So yeah, let me copy this one. This one cancels out, right? This one cancels out. Now this is ak 1 plus e raised to power minus 5 cot theta. Okay, so this is my actual answer actually. Okay, this is my peak, y of tp. Okay, this is my peak. Okay, so this is I can write like this one also equals to okay, I will derive this later. So like this is my peak, right? This is known as the overshoot, right? First overshoot. Okay, first overshoot. But there are many overshoots, right? There are many overshoots. So my overshoots are many. Okay, so they are basically like my overshoot, right? I can define them in terms of n, right? So this is the first overshoot. I can have second overshoot, third overshoot. Okay, so how will it happen? So I can, instead of writing only pi, I can write n pi here. Okay, because it was simply n pi by omega d, right? So this will be my y of t will be equals to ak 1 plus e raised to power minus n pi cot theta. Okay, and this is where these are the overshoot, and my n, right, n will not vary from 1 to 2 and 3, it will vary like this one, n will be odd. Okay, n will be odd. Okay, now what about my undershoot? Undershoot, it is the below value, like some value lesser than the steady state value. So undershoot, right, undershoot, it's y of t equals to ak 1 minus e raised to power minus n pi cot theta. Okay, but this time, right, my n will be even. Okay, it will be only even, it will also vary, but it will be even. So n will be even. Okay, or you can write n equals to 2n, something like that, because that will only make it even, and n belongs to 2n plus 1, so that will only make it odd. So yeah, this is my basically graph. So I will show you graphically also what I am talking about, right? So let me copy the graph, and there I will explain. Yeah, here is the graph, right? So basically, right, this is for n equals to 1, and this is for n equals to 2, and this is for n equals to 3. Okay, so these are what? These are the overshoots, right? These are the overshoots. And what are these? These are the undershoots. Okay, these are the undershoots. Okay, so basically this is what an overshoot and undershoot are, and graphically also I have shown it, right? This is n equals to 2, then it will be n equals to 4, like this. Okay, so I hope you understand. So now one more point I have to tell you is that like one more key point is that what is the time period of each oscillation, right? So between one overshoot to another overshoot, so like here I have one overshoot, right? At this point I have one overshoot, then I have another overshoot. So what is this value? This is pi upon omega d. So let me replace this Tp with pi upon omega d. Okay, and this one is this, what will be this one? This will be 3 pi upon omega d, right? Why? Because this is n equals to 3, right? N equals to 2 was here. Okay, at the undershoot. So at the overshoot it will be 3 pi by omega d. Okay, so this is n equals to 3 pi by omega d. Now, right, now like what do you mean by period, right? Period means it repeats, but here it doesn't exactly repeat. Okay, but what you can say, it repeats, it again reaches maxima, then again it goes down. So that is what a period I can define here, right? Okay, that's according to the definition only. So I'm reaching maxima, then again I'm reducing, then I'm reaching maxima. So I'm completing one period, I can say one cycle. Okay, but it's obviously not exactly equal to this peak, right? It is reducing. Okay, but still I can explain like this one. So my period of oscillation, okay, so time period of oscillation. Okay, so what is my time period of oscillation? So time period of oscillation will be basically one cycle. Okay, one cycle is 2 pi by omega d. Okay, so that is my time period of oscillation. Okay, then we'll also study the number of oscillations in a after it settles, right? Okay, after it settles, so like we'll find the settling time. Okay, then what we'll do is divide that with the period, and we'll find the number of oscillations. We'll see, we'll do one question, and from there we'll understand. So I just gave a hint because I wasn't supposed to say this to you, but still now we have to, well, the third parameter is the maximum peak overshoot. So what is the maximum peak overshoot? It is the normalized difference between steady state value and maximum value of the system response, right? So basically it is the normalized value of the, like the steady state and the maximum peak. So this is my maximum peak. Okay, the first peak, right? So this is my maximum T goes TP. So like let me write mathematically what does it mean, then you will understand it. So my MPU equals to simply y of TP, it is the maximum value, minus y of infinity by y of infinity. So also we define it like percentage also. So my percentage peak overshoot, this is normalized, right? This is normalized with respect to the steady state value. Okay, that's why the definition is stating the normalized difference. Okay, so yeah, I can write this is in terms of percentage also. This is percentage MPU equals to y of TP minus y of infinity by y of infinity into 100%. Okay, so yeah, this is basically my percentage MPU. Now let me derive it, right? So I know y of TP, that's why we found it out in the previous expression, right? So what is y of TP? Y of TP is this one, right? This one. So let me copy this one, and what is my y of infinity? Okay, in the graphs now I didn't write, I shouldn't have wrote here AK. I shouldn't have wrote it here 1, I should have wrote here as AK, right? So this is AK and this is also okay. I have to change all of this. So in the graph, like, okay, let me change this quickly. This AK, because steady state I'm generalizing it. Okay, I'm not just giving a unit step input and the gain of the DC gain of the system is unity. That I'm not doing, right? So it's for you only, because like sometimes in the question the input won't be unit step and the DC gain won't be unity. Okay, this is also AK. And this is also AK. So yeah, this is basically this one, and yeah, this is AK 1 plus this one. Okay, so yeah, now what is the steady state value? Steady state value is AK only, right? AK only. So I will put AK here minus AK. Okay, and then what I will do, I will just divide this by AK, because I am taking the normalized difference. Also I am calculating the percentage MPU, so this will be multiplied by 100. This equals to my MPU itself. Okay, equals to my MPU itself. Okay, so now let us write what is MPU equals to. So MPU, right, if I like divide this one, I get only this one is getting subtracted. Okay, if I take AK as common, I will have 1 minus 1 and I will be only left with this one, right? Because this AK and upper AP numerator AK will get cancelled out. So what I will be left with, my percentage MPU, right? Percentage MPU will be simply equals to e raised to power minus pi cot theta, okay, into 100%. Now can I rewrite this expression? So it may so happen that finding cot theta is difficult, but generally cot theta is finding easy. I will tell you why. But if you want to solve this in terms of zeta only, so what is cot theta equals to? Cot theta was equals to the inverse of tan theta, and tan theta was equals to simply omega d by omega zeta omega n. So if we write this in terms of omega n, it is under root 1 minus zeta square by zeta, right? But I have to find the inverse of this one because it is cot theta. So it will be e raised to power minus pi zeta upon under root zeta square. Okay, so this is my what my this exponential is equals to. So this is my formula. So I have to multiply 100 over here also, because yeah, this is percentage peak overshoot. So 100%, right? So this is basically my maximum peak overshoot. Now what things do I notice here? So if my zeta, like how is my maximum peak overshoot related with the zeta, right? Zeta. So if my zeta increases, okay, this numerator will increase, but this whole denominator, zeta increases, so this whole denominator, what I say, is will decrease. This whole term will increase, right? This whole term will increase. Now if this whole term increases, what happens? Then my e raised to power minus pi something increases, so this will decrease, right? This will decrease. So what do I understand from here? If zeta increases, my maximum peak overshoot decreases. So maximum peak overshoot is inversely proportional to the zeta, right? So this is also what we can understand, or from directly here also you can understand. What is my zeta? My zeta is directly proportional to the cos theta. Zeta equals to cos theta itself, right? So it is directly proportional to the cos theta. But what we know about cos theta, if theta increases, cos theta decreases. Okay, you check, cos 45 is 1 by root 2 and cos 60 is 1 by 2. So it is reducing, that is 0.707 and this is 0.5. So if theta is increasing, cos theta is reducing. Hence cos theta is inversely proportional to the theta, right? So if it is inversely proportional to theta, what can we say? Like then this, if zeta is increasing, okay, zeta is increasing, then okay, I can delete this from here only. Then this cos, like what is cos theta equals to? Cos theta equals to cos theta 1 sin theta. Then this cos theta will reduce, okay, and sin theta will increase, okay. Then okay, sorry, one more thing, zeta is increasing, okay, cos theta will reduce, yeah, but my theta, yeah, cos theta will increase and sin theta will reduce. So if cos theta increases, okay, like cos and sin are inverse of, I mean, like in terms of theta. So if cos increases, sin will decrease, right? So if cos increases and sin decreases, this term becomes increasing, okay, this term becomes more, hence this is a negative exponential, so this will further reduce, so my MPO will reduce. So if zeta increases, my MPO will reduce, so they follow the inverse law. Okay, that is enough. Now let me write the another performance parameter that we just have studied, that is the T rise, right? TR. So what is TR equals to? TR equals to pi minus theta by omega t. Pi minus theta by omega t. So this is what my TR is equals to. Now if my TR is equals to this one, so I've already found the relation between zeta and theta. So zeta and theta are inversely proportional to each other. So if my zeta increases, my theta will reduce. Now if theta reduces, this whole thing will increase, right? If this whole thing increases, then my TR will simply increase, right? But what another thing you have to keep in mind is there is omega d also here, okay, and that is also function of omega and 1 minus zeta square. Okay, so let me break it down. Basically this is pi minus theta by, let's say omega n is constant, you have to take something as constant. This is 1 minus zeta square, 1 minus zeta square. Now this theta, right? Theta, what I can write here is cos inverse zeta. Now if zeta increases, right, if zeta increases, then this one will decrease, right? This one will decrease, okay, hence this overall thing will increase. Now if zeta increases, this difference term will increase, decrease, and if the denominator decreases, then this will increase further, so my rise time will increase. Okay, so from there also you can understand. So let me write this in different color. Zeta increases, if my zeta increases, then what will happen? Then my theta will reduce, okay, and if theta reduces, then this bottom term also, okay, bottom term also what do you say, reduces, okay, because this increases, this whole thing reduces, and if this denominator reduces, then this whole upper thing will increase, right? Okay, if from 1 it becomes 0.95, then obviously the ratio, this whole term will increase, right? Okay, hence my TR will increase. So what I am saying is, like, these are directly proportional to each other, and MPO was inversely proportional to the zeta. Now what do I want a system? Okay, what do you want from a system? So if you turn on your fan, what do you want? You want it to start immediately to that speed that is desired by you, right? Okay, you don't want it to take too much time. So what does that mean? You don't want too much rise time, right? Okay, like there are many other time parameters also, but just taking an example. Okay, you don't want too much rise time. Now what else do you want? you don't want it to go too much beyond your speed initially at the starting stage, because what happens initially when the fan starts, it has to provide a starting torque, which is it takes huge amount of current, right? So it has to provide huge amount of starting torque. So it may so happen it goes over its settling point, right, over its final value. So you don't want it to go too much over its final value, right? So that is what basically MPU is. So obviously you don't want very high MPU, but you don't also want very high rise time also, okay? But what is the problem? To reduce MPU, you have to increase the zeta. To reduce rise time, you have to decrease the zeta, okay? That's why there has to be some compromise, okay? That's why in general we keep our damping factor between 0.4 to 0.8, okay, for designing purpose. This is just a general rule of thumb, okay, to keep my MPU and zeta, both of them like balanced, right? I don't want any one of them to go very high, okay? My zeta zero 0.4 to 0.8 for like balanced MPU and TR. Why? Because my TR is directly proportional to zeta, but my MPU is inversely proportional to zeta, and I want both of them to be low, right? So yeah, this is one case. Now let's study the delay time, right? What is the delay time? So the delay time is basically the time taken for the system to reach from 0% to 50% of its final value. This is again valid for the underdamped case. So like again we'll derive it, okay? We'll not derive it actually, because this is okay, we'll not derive it because this will take time. We have an approximate formula, okay? The formula is for delay time is basically my TD. So like everything we won't derive it, 3 things you have to remember. So there are like more than one approximate formulas, but we'll use this one only. That is equal to 1 plus 0.7 zeta by omega n equals TD. So this is between zeta 1. So like this is basically the first order approximation, right? This is also known as the first order approximation, okay? So yeah, this is basically my delay time, okay? I won't go into details, but next one is my settling time. What is the settling time? Basically settling time is the time taken for the system to reach 0% to some percentage of its final value within the desired error band, okay? So like it has to reach within the error band, right? Like in the first order system it was easy to find the settling time, because what happened was there was no oscillation, right? So it was reaching the settling time only for once, the settling value only for once, right? Here what is happening, sometimes it is going above, then down, then again going above, right? So that is an issue, right? That is an issue, because like I may say that the time it reaches 98% of its steady state value. Here also it reaches 98% of its steady state value. Here also it reaches, right? But here it didn't settle it. It settled somewhere around here. So how we define it? We define it like it is lying, like my output response is lying within some error band, right? So output response must lie. Okay, let me use another one. Okay. Output response must lie within this error band. So this is known as the error band, okay? This is known as the error band. So output has to settle within this error band. That's why we tell it, right? Now from here you can define, yes, it has to settle, right? If it is lying within this error band, then it has settled. So what is the desired error band? The desired error band may lie somewhere between 2% to 5%, right? 2% to 5%. Now we will only study two error bands, that is one for 2% and one for 5%. Okay, those two are most important. Other ones you don't need to remember. Okay, so I will make a table over here. Make a table quickly. I will do it for two systems. One is for underdamped and one is for overdamped, right? So one is for underdamped and one is for overdamped. So basically this is my error band, this is my T-settling, zeta 1. Okay, and like this T setting is for underdamped. Okay, I will write here is underdamped and this is for overdamped. Okay, this is greater than 1. Okay, so yeah, this is basically write the table. So if it is within my 2% error band, right, 2% error band, okay, 2% error band, then what will happen? Then it will be simply equals to that same formula, 4 tau only, right? So you don't have to remember this, just remember 4 tau. Okay, for first order system also I told you 4 tau, so remember just 4 tau, that is important. Now what is tau? Tau is changing, right? For first order system, what was tau? Tau was the inverse of the pole. Okay, just that pole. Now what is the tau, what is that like tau for here? So tau for here, right, 4 tau. Tau for here is basically the negative inverse of the real part of the like pole, right? So it is zeta omega n, right? So zeta omega n is lying around here. Okay, let me draw it. So omega d was the imaginary component and zeta omega n was lying somewhere around here, minus zeta omega n. Okay, so this one, right? So if I take the negative inverse of this one, so I will get my tau equals to tau. So this is 4 by zeta omega n. Okay, so yeah, this is what equals to tau is. Now what is my tau for zeta greater than 0? Okay, so I have only one pole, that approximation, right? So I again wrote it previously also, the tau value. Okay, I will again write it. So it is 4 tau again. Okay, 4 tau again, and this is equals to my 4 upon zeta omega n minus I don't have space, I think I have to make this smaller. Zeta omega n, I have to remember what was this, minus omega n zeta square minus 1, right? Okay, so this was my like pole basically. Okay, so this is for the case of 2% error band. Now what is for the case of 5% error band? You tell me, right? You remember for the first order case what was the 5% error band? It was basically what? It was 3 tau, right? So 3 tau. So I hope you understand why it is 3 tau, because it is less, right? Obviously it has more headroom, right? More headroom. So it obviously, that's why this is 3 tau, because this is less time. It will reach within this 3 tau, like more error band in lesser time. This error band is reducing here, right? Okay, but if I make the error band broader, then obviously I will reach within my error band in much lesser time, right? So yeah, this is equals to 3 tau, and this is like again this one will be same, only just instead of 4 it will be 3 this time, right? So let me copy this one, and instead of 4 it will be 3. So yeah, this is basically this one, right? So we are done with this parameters. So let us just get a quick recap, right? So what did we study? So firstly we studied about the rise time, right? So rise time, this one is for overdamped definition. It is basically first time it is reaching 100% of its steady state value from 0%. So we derive, and for critical damped it is different. For overdamped it is similar to the first order system only. So rise time we derived here, we got our answer as this one. So this you have to remember. Okay, how you remember? So basically, right, what do you do? So you have to make this one 0, right? You have to make this one 0. That's why the term something like this one comes. Okay, that's how you remember this one. Okay, you make this sine theta 0. Okay, from here you make this one 0, and like if you make this one 0, what do you get? You get your AK itself, right? So you have to make this one 0. Okay, and how you make this one 0? Obviously you can't make t equals to minus theta upon omega d. That will be some negative value of time, which is not possible. Obviously our system gives output after t equals 0, so that is gone. But what is the first peak? First peak will be basically this like not the first peak, like what will be the value for which this will again go to 0? It will be pi plus theta. That is basically pi plus this omega dt plus phi. I mean pi equals to this omega dt plus phi theta. So that will be t equals to pi minus theta by omega d. So that's how I get, right? So that's how you remember. Okay, quickly, that's how you quickly remember this. So yeah, that is for the rise time. Then I told you, like, just be careful if they have asked you the rise time for overtime system, just don't blindly put that in the formula. Okay, check, okay, if something weird is coming, so you have to use the formula for overtime. Okay, so we calculate the rise time for overtime system. Now we did for peak time, right? What is my peak time? Peak time basically is the first time it is reaching its peak, right? Okay, this is the maximum peak that it is reaching. After that it is obviously decaying due to damping. So we again differentiate, right? Differentiate and find the peak time. But if graph wasn't present, we have to do double differentiation and check, okay, if my value double differentiation is coming positive or negative at that peak time. It should come negative, right? It should come negative for maxima and positive for minima, right? So that is basically that one. And these are my peak times basically. Okay, so yeah, we have multiple peak. Basically this is the first undershoot. For even n I will get undershoots, and for odd n I will get overshoots. Overshoots mean some value above the steady state. Undershoot means some value below the steady state. Okay, so this is basically my overshoot and undershoot. Now we have to like calculate the maximum overshoot, the value of the overshoot, right? I calculated the time at which the overshoot occurs, but I have to find the value of the maximum overshoot. So for that I found out the value of the maximum overshoot. Okay, so that I got. Now like overshoot I got here, okay, and undershoot value I got here. So this you don't have to remember this, but the MPO term you have to remember, right? That is important. So this just for the derivation I told you, okay, but this still you can remember, right? This is simply just AK times this 1 plus e raised to power minus n pi cot theta. So this is 1 plus e raised to power minus n pi cot theta. So you understand, right? This is plus 1 plus, so this will be overshoot, and this is 1 minus, so this will be undershoot, right? So yeah, this is this one. And like here I told you all those things. And the one term is also time period of oscillation. So this one also you have to understand that obviously this is not perfectly periodic, because obviously my values are decreasing, but at this I'm following some pattern, right? So I'm again reaching my maximum, okay, local maximum here, okay, then it completes one complete cycle, right? So that's why this is what is this time period? This time period is 2 pi upon omega d, as this is pi upon omega d and this is 3 pi upon omega d. So this will be 2 pi upon omega d. Okay, so now we have to find the maximum peak overshoot basically. So maximum peak overshoot is basically the normalized difference of the maximum value, peak value, and the steady state value, right? So it is ytp minus y infinity divided by y infinity. Okay, so yeah, this is gone, and I get my MPO as this one. So this formula you have to remember, there is no alternative. So this is you have to remember, okay, and that maximum overshoot, right, that also you remember, that is also important, right? So this one is also important. Okay, this one, these are important, so I will put them in some box. Okay, and I think you can remember this, so I hope so. So this here remember, okay. So here also this you have to remember, okay. So if you remember that one, you can derive it here, okay, and if you remember this one, then you can derive there also, okay. But this is easy, right? If you want to write it in terms of theta, you write e raised to power minus pi cot theta, and if you want to write in terms of zeta, you can write this one. So why am I writing two forms? What is the importance of this one? So this is basically important for gate calculator, right? So in gate calculator, what you can do, if you have zeta given, right, if you have zeta given, you instantly do cos inverse of that one, and you find theta. Then what you do tan theta, okay, then you find the inverse of that one, so you find cos theta. Now you multiply pi and then minus 1, okay, then you do the exponential power and you get the value, right, get the MPO. Or you have to do this one also. This one is a bit messy, but this one also you can do. What do, you find zeta square, okay, then 1 minus zeta square, then under root that, then zeta by under root 1 minus zeta square, and you get this value, okay, then you do minus 5 multiply and then again exponential power. So that also you can do, okay. So whichever you see, whichever you are getting a good grip at, you use that, okay. So that is why I told you in two forms, right? So two forms are important, okay. So yeah, this one was one thing, and then I told you the relation between MPO and rise time. Why? To have a basic understanding of designing, right? So in designing you have to keep few things in mind. So this is one of the things in mind. So that's why, like, I can't increase my zeta too much or decrease my zeta too much. So if I decrease my zeta too much, my MPO will increase, which I don't want. Obviously I don't want my fan to like totally blow away from my desired value, right? That I don't want. Also I don't want my fan to be too much slow. I want it to rise, okay. I want it to get my desired value in my time, right, in some time, not too late, right? So yeah, that is what TR and MPO is. So I have to find a perfect balance between these two. Then we studied about delay time. This is not just another parameter, so you have to remember this one, okay. This is not, you have to remember this one, okay. I'm sorry for this, you have to remember this one. This is 1 plus minus 0.7 zeta by omega n. What you have to keep in mind is here it reaches 0% to 50% of the final value. So how to remember this? In terms of in case of that rise time, right? In case of rise time, what was happening? My rise time was equals to pi minus theta by omega d, okay. Here everything has changed. In the denominator I don't have omega d anymore, I have omega n. So that's how you remember. So in the denominator I have delay time as omega n, okay, that is gone. Then in the numerator I don't have any theta pi, I have simply 1 plus 0.7 zeta, okay. That's how you remember. You find the differences between the rise time and the delay time, right? So this is the difference, okay. So yeah, this is just an approximate formula, okay. So you remember this. Now the settling time, right? Settling time is basically within the error band, and this is easy to remember. Just remember two formulas. For 2% error band it is 4 tau, and for 5% error band it is 3 tau. That you remember. Now what is tau? Tau is the negative inverse of roots, real components of the root, right? So for this one it is 4 by zeta omega n. I know the real component lies around somewhere here, and for t settling it is 4 upon zeta omega n minus omega n under root zeta square minus 1, okay. So this is this one, and this is 5, like for 5% error band this is simply 3 tau and 3 tau, right? 3 tau and 3 tau. So again tau, right, you put tau equals that. So you don't have to remember this, just remember for 2% error band it will be always equals to 4 tau, and for 5% error band it will be always equals to 3 tau. And tau, you know where the roots lie for the overdamped system and for the underdamped system and for first order system also. Yeah, that is it. Now I will give you homework, few assignment questions, and in the next lecture obviously we can't do the performance parameters by varying the poles. That we will do in the next lecture also, analysis of performance parameter by varying the poles, and the assignment question also. So this is question 1. Take the screenshot and find the answer, right? This is also a gate question, okay. All these are gate question actually. I forgot to write the years. So yeah, just take the screenshot. Yeah, this is a bit different question. Take the screenshot or pause the video, whatever you want to do, and then try to solve this one. You have to find all of these parameters, right? Okay. So yeah, I think that is it. I think those are all the questions. Yeah, those are all the questions. So yeah, I will see you in the next lecture. Thank you for watching.